All right, so a question like this one, guys, okay, still a work energy theorem question, but this one is also designed to explain why a ramp works, okay, or what a ramp actually does, okay? Why did we invent the ramp? What does it do? It makes work easier, okay? It makes work easier because if I have a ramp, I have two ways to get something to the top of it, okay? So if I have this ramp here, okay, my two options for getting something to the top of the ramp would be to lift it directly over this distance or to push it up this distance. Okay? Either way, when it gets to the top of the ramp, it has the same amount of energy. Right? Everyone okay with that? Okay, so it's the same amount of work to get something to the top of the ramp either way. What makes a ramp useful is that I don't have to exert as much force going up the ramp as I do to lift it to the top. Right? Because if you recall, work is a change in energy. Okay, in this case, we're talking about a change in potential energy because we're changing the height of the object. Everyone okay with that? All right, so this number is the same regardless of whether I lift it or push it up the ramp. What's different are these two numbers, force and distance. Lifting it to the top of the ramp is a shorter distance and thus requires greater force. Pushing it up the ramp is a longer distance and thus requires less force. It doesn't make less work, it makes the work easier because you don't have to push as hard. In fact, it may make the work possible versus impossible, right? If we're like, the ancient Egyptians and trying to build the pyramids without the help of aliens, because they didn't have help of aliens, okay? They had lots of sand and thousands of slaves, so they built really, really long ramps and made the slaves drag the rocks up the ramp, okay? They didn't have enough slaves to have the slaves lift the rocks up to the top of the pyramids because that would have been impossible. The rocks are the size of a small apartment, okay? So we wouldn't have been able to do that, okay? Instead, they just dragged them up these ramps. Usually they had like logs and stuff underneath. But anyway, it was dragged up a ramp, okay? Because that way they could exert enough force to do it. Does that make sense? All right, so in this question here, they're telling me that I'm using 150 newtons of force along a 25-meter ramp. So they've told me force and distance, and they want me to figure out how much higher the box is at the top of the hill. All right, so now I've got to address the other side of this equation. I've got to say that force times distance equals m times g times h final minus m times g times h initial. Since this is starting at the bottom of the ramp, what's my initial energy? 0. Okay, so I can just eliminate then that part. All right, so I have force, I have distance. They told me the mass. Okay, they said it's a 35 kilogram box. And I always know what g is, so can I solve for h? Just divide both sides by mg, and I'm solving for h. Okay. Guys, basically these work energy theorem questions always come down to essentially the same steps. Okay, I identify what kind of energy is being changed. I set force times distance equal to it if I have to. Okay, and then I manipulate for whatever it is I'm looking for. All right, so in this case here, we'd be plugging in our numbers. That would be 150 times 25. Okay, that's our force, that's our distance. Okay, divided by 35, our mass, times 9.81, the acceleration due to gravity, okay, and I'll have my answer. Go ahead. Yeah, that's good. 10.9 meters. Okay, so the height of the ramp is 10.9 meters. All right, everybody okay with that? Okay, so like I said, there's basically a kind of a given set of steps for all these work energy theorem questions. So I want you to write those steps out. Okay, so if we're solving a work energy theorem question, we are dealing with work changing mechanical energy, either kinetic or potential. That's force times distance is a change in mechanical energy. Okay, write out your givens, identify the type of energy being changed. Is it potential or kinetic? Okay. Second step, set up the work energy theorem, okay, which I've done in basically every question we've done. Set work equal to the change in energy, okay, and then manipulate and solve. Okay, so let's walk through this one using the steps that we wrote down just a minute ago. Okay, first thing is we write down our givens. We know that the force involved is 10,000 newtons. Okay, we know that it slows from 20 to 6 meters per second. So that means our initial velocity is 20 meters per second and our final velocity is 6 meters per second. All right, and we know that the car's mass is 1,700 kilograms. All right, so in a question where the context is a car slams on its brakes, what kind of energy is being changed about the car? It's kinetic. It doesn't mention anything about it going up or downhill, so it's just kinetic. So that's our next step. We've identified that the work done is changing the kinetic energy of the car. All right. That means if we expand this out, we have force times distance equals 1/2 mvf squared minus 1/2 mvi squared. Okay, and we are trying to find how far the car will travel. So how do I get d by itself? I divide by f. Okay, that'll get me my distance traveled. I have a value for m, vi, and vf both have numeric values that are not 0, so I can't, cancel anything off here. Okay, this is the formula that I now need to use. Now, the one thing I do need to keep in mind is that the car is losing energy in this one, not gaining it. So is the work positive or negative? It's negative. So this number here is actually a negative number. All right. If you don't make that negative, then you get a negative 30.9 as your answer, which means the car went backwards as a result of slamming on the brakes, which isn't necessarily true. Okay. Well, it's not necessarily true. It's also not true at all. Okay. Because it obviously doesn't do that. So we plug in our numbers here. We got 1/2 times 1,700. Okay. Times 6 squared minus 1/2 times 1,700. Times 20 squared, divided by negative 10,000 newtons. Okay, so 0.5 times 1,700 times 6 squared minus 0.5 times 1,700 times 20 squared, okay, divided by negative 10,000. All right, 30.9 meters is how far the car will travel before coming to a stop. Okay, so did I follow the steps that I listed there before? Okay, I wrote down my givens. I identified the type of energy being changed. I set up the work energy theorem. I manipulated, solved. Okay, exactly the set of steps that I had written there on the previous slide. If you follow those steps, you really can't go wrong with any work energy theorem question, including what you would get in physics 20. Okay, in physics 20, when you do this, you'll have both kinds of energy changing. There'll be a change in both potential and kinetic energy at the same time. So something is accelerated up a hill. So it's gaining both potential and kinetic. Okay, it doesn't really make it any harder. You just have to remember there's both kinds of energy. Okay. All right, you won't have to do those in Science 10, okay? But it's still the same set of steps. All right. Let's have you guys try this one here with the slingshot. Okay, so we got a slingshot and it's aimed straight upwards, drawn back 0.4 meters using 1,500 newtons worth of force. The rock reaches a height of 30 meters. We're going to assume the person is lying on the ground. So the initial height is 0. Okay, we're looking for the mass of the rock in this one. All right, so for this one here, first thing, our givens. Okay, we know the distance that the slingshot is drawn back is 0.4 meters. We know the force used to do that is 1,500 newtons. Okay, and we know that the rock reaches a final height of 30 meters when its initial height we discussed was 0 meters. All right, so we're looking for the mass of the rock. All right, what kind of energy is being changed in this question? Potential. Okay, I mean there is a change in kinetic as well, but we're not dealing with that part of it. We're only looking at from ground to its maximum height. Okay, so we are looking at delta EP here, okay, which will mean force times distance equals m times g times h final. There's no need to write mghi because hi was 0 anyway. All we're doing is manipulating for m, so that'll be g divided by, or g and hf, divide both sides by those. Okay, plug in our numbers. So we got 1500 times 0.4, okay, divided by 9.81 times 30 meters, and that'll give us our mass. So 1500 times 0.4 divided by 9.81 times 30. Whoop. All right, so it's going to have a mass of 2 kilograms. So it's a big rock. All right, is this starting to make a little more sense than it did the other day? Okay, I mean, once you have kind of a set of steps to follow, it makes them a little bit easier to deal with. All right, so, okay, try that one. Similar to what you just did, except this time there actually is an initial height. Okay. All right, so in this one, okay, we don't have the force times distance part on this one. How do I know that? Right, because they told me what the work was. They told me it's 4,000 joules, and they're not mentioning anything about distance or force here. Okay, so I know I don't have to deal with that part of it. I know that the work is 4,000 joules. Okay, I know that the mass is 25 kilograms, and I know that the final height is 7 meters. Or sorry, the initial height is 7 meters, sorry. And we're looking for the final height. All right, so work's a change in energy. In this case, it's a change in potential energy because we're changing the height and not the speed of the box. All right, so that's going to be that work equals m times g times h final minus m times g times h initial, and I'm looking for hf. Okay, so what should I do with mghi right now? Add it to the other side. I got to move it over, okay? Because work plus whatever I had at the beginning will equal what I had at the end, okay? That's what I'm doing by moving that over and adding it. So the change in energy plus the initial energy, which is what I have here, equals the final energy. All right, I don't want the final energy, I want the final height. So I'm going to divide both sides by m times g. Okay, that comes over here. It doesn't cancel. Okay, it doesn't come out of there. Okay, we're looking for HF. All right, so now we'll have our 4,000 joules plus 25 times 9.81 times 7 divided by 25 times 9.81. And that should give us 23.3 meters, okay, as the top of the ladder. Amanda, question? Comprehend? Okay, where did I lose you? Okay, copy it down and then I'll find out where I lost you. Okay. Any other questions on that one? Okay. So, like we said, guys, we're just following similar sets of steps each time. This time we didn't have to do force times distance. If we did, it would have been right here. Okay, we would have just written force times distance plus m times g times h. It wouldn't really have changed what we did. Okay, so initially here, I said that work is the change in energy. Okay, I didn't want the change in energy. I just wanted the final energy by itself. So I added the initial energy over. Okay, so I added this whole term over to the other side, which I can do because according to order of operations, before I would subtract these two numbers, I would have done all the multiplying. Okay, so really, I'm just taking this whole number over to there. It's really just one number according to order of operations. Okay, so I move it over here. Okay, then I have work plus the initial energy, okay, equals the final energy, and then I just isolated HF by dividing both sides by mg and bring it over here. Okay, that's all I did there, just manipulation and solving there at the end. Okay, take a little break, then we'll try this one.